Is that okay with the sound and everything? Yeah. Yeah. Okay. So we had an introduction on micro scale engineering, on process intensification in the morning. So the second lecture now is going full speed to talk about two-phase flows and flow patterns in small channels. So the whole idea, as said with the slide I showed you about the program structure, is that we'll talk about the hydrodynamics first of all, and effects of properties of channel sizes and wattability, and then we'll go to actually looking at applications like separations or reactions in the small channels and scale out. So the hydrodynamics, the first part of the hydrodynamics, we talk about two-phase flows in small channels. And very quickly, to just set the scene as well, multi-phase flows can involve 2 or 3 phases. What I will say from now is that we are looking, what I will show you here is referring to 2 phases, liquid-liquid or gas-liquid. Start with some reference to gas-liquid and then move to liquid-liquid. And there won't be any reference to solids. So just bear that in mind when we go through this presentation. So yeah, but you know, many processes in large and small scale systems involve 2 or 3 phases. When we have more than 2 phases, more than 1 phase in channels or in process units, then we can have different flow patterns, flow configurations, which we call flow patterns. And as I said, I will start with some work on gas liquid flows, and then we will move to liquid ones. So again, going back into forces and what we were mentioning in the morning, in general, in gas liquid systems, we can divide the patterns into these 3 main, let's say, categories. This is a what we call a flow pattern map, where we try to show in which areas the different patterns appear. And a very straightforward, simple flow pattern map is where we use the velocities of the 2 phases as coordinates. There are many ways to use the velocities. We can perhaps discuss that if you want. One is to use what we call the superficial velocities. I don't know if people are familiar with this term. Yeah. Can somebody say what it is? Say that again.
Area where velocity to that particular phase only at that cross section.
How can you calculate it?
That area, at that cross section.
So
That phase only.
yeah, not quite, unless I didn't understand it correctly. So anybody else, what is superficial velocity?
Only that gas or the fluid
It's flowing through, yeah. So it's basically volume rate, flow rate of this phase divided by the whole area of the channel. Yeah, so this is superficial. So it's not the actual velocity. If we knew the actual area that our phase occupies and we divided the flow rate with that particular area, then we would have the actual velocity. Very often in multi-phase systems, it's very difficult to know in situ what is the actual area occupied by a phase. And that's why superficial velocities are used. Superficial velocity is basically a flow rate, and not non-dimensionalized, but with a reference to the area, to the channel. It is applied. So in this, let's say, flow pattern map, we have the flow patterns that are surface tension dominated at lower velocities. Then there is some transitional patterns. I'll come back to this. And then there is the patterns that are dominated by inertia. And this is the annular flows and the dispersed flows. So when we have very high gas velocity, then the annular flow forms that there is, you know, an annulus, a core of gas with a film around it. And when we have also quite a lot of liquid, then we go into dispersed flows. And the surface tension dominated ones are the Taylor flow, yeah, that we will talk a lot more about it. I have some images as well. and the bubble flow when we have a lot of a small amount of gas, but a lot of liquid. And what I mentioned here in this transitional is that all these transitional patterns usually occur in the boundaries between the main flow patterns. And when the flow has characteristics of both types of patterns. What we have seen though in small channels is that these patterns can occupy quite a large area in the map. That's why perhaps they deserve a special mention. In microchannels, we will see more this tail or annular flow. We have some schematics figure in a minute. Churn flow is a little bit more difficult. Churn flow is like in between tailor and annular flows when the flow is quite mixed. You have to have quite high velocities and a lot of liquid to see that. It's more common in larger channels.
So flow pattern is for both vertical and horizontal channel.
Sorry, both?
Horizontal.
Yeah, I have not done any definition here. This is very general. It's not even any numbers. But yeah, you can say that it doesn't matter if you are in small scale, whether you are horizontal or vertical. But of course, this is not entirely true, especially if we move to bigger channels. Just again, some definitions, because these numbers, they will come in sometimes in the representation of the flow pattern maps. I've given the definitions here very general. We can discuss them, but I will say what I mean by very general. So Reynolds number, I guess everybody is familiar with Reynolds numbers, yeah? And is inertia over viscous forces. So it can be important because, yeah, we can have inertia at high velocities, especially with gas phases. We can have viscosity effects, of course. A very important number is this capillary number, yeah? Which is the viscous over the surface tension or interfacial tension forces, surface forces in general. The bond number, we just saw it before. Yeah, I mentioned it here. It's the effect of gravity effectively over the surface tension forces. And then there is this Weber number that, yeah, you can obtain it from combining, let's say, different types of numbers as well. But so this is a mistake here. So this should be inertia over viscous force. I'll correct that. So you can say that these numbers are equivalent if people have worked with dispersed flows. When our flow rates are low, the capillary number is more important because viscous effects are more important. When the flow rates increase, then the inertial forces become more important. So the Weber number takes over. Some correlations for predicting drop sizes actually in dispersed systems have either the capillary or the Weber number. Usually in stirred vessels, the Weber number comes in. But of course, if we have a high viscosity, the capillary number can be important as well. So these are alternative numbers people have used to also represent flow pattern maps. And what I said here is that this is just general definitions, is that all these numbers are very well defined. Of course, when we have a single phase, it's very easy to say what is the Reynolds number. But when we start dealing with more than one phases, there is always some sort of, we have to define how exactly we calculate these numbers. Because we could have a Reynolds number based on one phase or on the other phase, based on the actual velocity or the superficial velocity or the mixture velocity. And the same applies with all those. Okay, surface tension. I added gamma here as interfacial tension because we are going to talk a lot more about liquid-liquid systems. But is again, the conventions can be, the symbols can be, you can find both of them in the literature. I tend to use sigma for surface tension, gamma for interfacial tension, if they both need to be used in the same paper, let's say. But you can find both these symbols. So yeah, and the same, of course, with all these numbers, apart from this one here, that you have to decide or you have to tell us how you have calculated your number. And when you go to two-phase flow papers in microchannels or in large channels, it's good to pay attention to how exactly they have calculated the Reynolds number, because the definitions can vary. Not the definitions, the way they implement the especially these parameters, the velocity, and sometimes maybe the characteristic diameter here. And with capillary numbers as well. And again, if you have two faces, you can define them either from one or from the other, from both, give them both. Yeah?
What the effect of the surface of the material?
It's usually, yeah, very good point. I think there would be the whole lecture on that. We don't have it on dimensionless numbers.
No, have an impact on these values, or they are independent?
No, here these are calculated independently. There is nothing to give you contact angle, for example. Yeah. Okay, some flow patterns here, and I have used a lot of results from literature in this point. I hope you can see them well. So just what we mean with the various patterns, you may have come across them. This is bubbly flow. This is Taylor flow, and actually give you the difference. The Taylor flow, when we have gas liquid, it could have bubbles and drains. In liquid, they're more clean, let's say. Taylor annular flow, if you can see this, that's what is called Taylor annular. You actually have like a bubble, then like an annular, and then a bubble and continues. That's why even though it's a transition, a regime in between two regimes, it can survive for a large area of the map. And then annular flow, you can't really see it very easily here, but there is a film and the main core annulus. And there is a dispersed flow that perhaps from visual observations, we cannot see much. And what I wanted to now show you is that there are a lot of references here. It's worth checking them. A lot of things play a role on what is this, what flow patterns will form under different conditions. And coming back to your question, actually, is that in this case, just by treating the tube in that, so here it was not very well treated or not treated, so there might have been some impurities. Here it was the quartz tube was cleaned very well with ultrasound in a pool of pure water with ethanol and acid, and they did manage actually to affect to have an effect on the flow patterns with this carefully treated tube. You see here, we avoid having the formation of these little bubbles. The shapes are more clean, especially in the case when we had these smaller bubbles. So definitely wall effects are important. And what I will show you now is some different attempts to have flow pattern maps. I would say flow pattern maps, pressure drop in two-phase flows is like a holy grail. A lot of people are trying to they do experiments. This applies also to large-scale flows if people come from this background. They try to put their observations in a map, and this is true for this particular system, either tube size, material, fluid properties, even inlet conditions. And of course, what we all want is to have a generalized way to predict the flow pattern transitions. Because depending on which regime we are, the mass transfer will be different, the pressure drop will be different, whatever other properties we want will be different. So to be able to predict the transition lines is a very important thing. How easy it is that though? Not very easy. So I have here shown you a few cases where people have kind of tried to do that. So this work here tried for a large range of tube sizes, which are quite small actually, and that was for gas liquid flows as well. And you remember we said that perhaps this size we can still consider the effect of gravity not so important. These are the transition lines for horizontal, the solid lines, and for vertical flows. I won't go into the details. There is a lot of work discussed in the papers. Why is that happening? What I wanted to show you is that indeed there is difference. Okay. So, and this is the, let's say, straightforward flow pattern map where we have the superficial gas and the superficial liquid velocities. And this paper, a very nice paper by Coleman and Garimella, what they try to do is to explore the effect of the channel size on the flow patterns. These are all this is in a way scale up. When we do scale up, that's what we want to do, to change the channel size and still be able to predict what will happen. And so they had some main effects they saw is that by decreasing the channel size, the stratified flow was suppressed because interfacial phenomena take over, and we basically in very small channels, it's very difficult to get stratified flows. And they observed a larger area of Taylor flow, which when we go to talk about mass transfer later on, it's kind of beneficial for us. Again, a lot of different tubes, they went from 1 to 5.5 millimeters. And you can see, okay, the regimes appeared in the right area of the map, let's say, but you could have, this is the big tube, and this is the smaller one. You can see in the transition lines, there are a lot of differences. Something we did a few years ago with the students is that we tried to, and we published this work, is to see if by using predictions by some researchers, we used here the what Hassan and Tal suggested, could we actually, some people had done the work and they said these are the ways to calculate the transitions between regimes. Could we actually use these predictions to new situations, to new cases? And we use them against results from two other researchers, one at a small tube, 250 microns, and the other at a larger tube of 2 millimeters. And what we did is that we represented the main flow patterns that we can see in gas liquid flows. The Taylor flow, which is the T, the angular, which is the A, wavy, so there might have been some stratification in some cases, wavy stratified flow, double flow, and this churn flow, which as you can see appears at very, very high velocities. And you see here how good or bad the predictions were. Again, there is a good discussion why that happens. But having a simple, let's say, system of coordinates here, the superficial velocities, and using these, what Hassan suggested, we see that, actually Hassan had only one transition line between Taylor and annular flow, while we also pick up this different regime, the Taylor annular. And the predictions here are not terribly good. And we did the same with two other of the predicted, let's say, transitions by Akbar and Wellesley and von Rohr. And they suggested in their predictions flow pattern maps that were using the Weber numbers and the Reynolds numbers. So different ways to try to do that. People try by using the dimensionless numbers to see if they can actually make all these lines collapse, which is what you want for a prediction. To have all your prediction lines for whatever appropriate system of coordinates fall at the same location, because this means it's a good predictive tool. And you can see here that, again, in some cases, the prediction is not too bad. In this case here, they also had this difference between Taylor and Taylor angular flows, but some other areas are not predicted very well. And this is an even more complex system proposition. It includes both Reynolds and Weber numbers, while this is just a Weber number. And again, you see it's less lines, but okay, we see how well they do. So the outcome of all this is that there's still work to be done. Just generally for flow pattern transitions, it does look it doesn't look possible that all flow pattern transitions can be predicted by using the same dimensionless numbers, because it's different phenomena that expressed this that are responsible for this. Not for all flow patterns. So what I was saying is that it's probably as a step further. So this is one level. Let's try to do some flow dimensionless numbers or even simpler coordinates, and we predict everything. It's simple, it's easy to use. But the next level is to try to go back to physics in a way and to see what is responsible for this transition from one pattern to the other. So if you are, for example, either in a core flow, core annular flow, or they might have instabilities that cause this change to Taylor flow, or in stratified flows that there is a lot of work in large scale channels. There is a lot of work on instabilities that induce, they start this transition to another pattern. So this is the next step, let's say, or then it's CFT simulations. But at the moment in small channels, we are more or less here. Yeah.
So if we obtain the flow regime, flow pattern for say horizontal, while it is maintained, if we change the orientation, would it change, shift to the another type, or need to obtain it entirely in the horizontal?
So if gravity is not important, it should not. What I was also going to mention is that in a lot of in large scale systems, it's not considered so much, although it does matter. In small scale systems, it's even more important is the inlet conditions, the effect of inlet conditions. So all of these studies here, they don't use identical inlet conditions. And the inlet might play a role. So when you change orientation, apart from gravity coming in and certain symmetry in the flow, it could also be the way your inlet conditions are changing. So I would say you can assume if gravity bond number is low, should not play a role. It should be the same. So if you have Taylor flow in horizontal, it should be Taylor in vertical. But if you're very skeptical, you need to check that. Yeah.
So, but if the inlet conditions in horizontal and vertical can be different to obtain this, then how can actually we compare this part?
You compare because nobody mentions. It's very difficult to find in literature exact details of the inlet conditions. It's just that it's also something worth considering. Yeah, if you can, it's an extra, let's say, uncertainty. Yeah. And in a way, maybe if we want to discuss that towards the end of the course, we can discuss the effect of uncertainty. That there can be predictions by incorporating a certain degree of uncertainty to what we can predict. Most of the work has not been done based on the inlet conditions, it's based on what people see in the main channel, but the inlet can play a role. And what I'm saying is that it's even more important in small channels because of not only because the inlet can be quite comparable, but also because the development lengths are, we use much shorter, let's say, small channels than in a proper large scale system, thinking of pipes, for example. So this is, if people are interested in doing work, this is an area that people could do a lot more work. So it's always worth having it in mind. I will now move to liquid-liquid, which is, and I show you the experimental setup here because in the beginning I was thinking I will just talk about liquid-liquid flows, but I thought just to give an overview on where we are, it's worth mentioning the gas-liquid flows, especially because liquid-liquid is, the study started kind of later, and a lot of the, let's say, ideas, concepts, like of the dimensions numbers even that people use for the flow pattern maps, come from gas liquid. Even some of the descriptions I'll give you for Taylor flow later on originate. People start from gas liquid flows and then they move them on, try to use on liquid liquid flows. So this is a typical experimental setup. Don't know, do people here work with microfluidics at all? Show of hands, have people worked with microfluidics? 1, 2, 3, 4. Okay, just to get an idea. So do people have people seen experimental setups of microfluidics? You will have a chance, I think, in your tutorials. But it's quite simple. You have two pumps, which are for this scale also quite often syringe pumps. And you bring your two fluids. In this case, it's two liquid phases, an organic and an aqueous, or an oil and the water, at the inlet of the test section. And the inlet can be a lot of different things, can be T junctions, Y junctions, cross junctions, flow configurations. And then simple first experiment for flow patterns is to observe with imaging. And I think you are doing a tutorial as well based on that. A lot of work, how do we image, how do we get a account of the various effects? But basically we see the flow patterns, especially, and that's why, especially in the lab, at least initially, tubes tend to be transparent. And then there is an outlet, and then things can happen. If we have a reaction, we might collect to study concentrations or whatever else we want. So this, of course, is not exhaustive. There is a lot of work on flow patterns in small channels with liquid-liquid. I mentioned some references. I'll show you some of our work because I have the better images from there as well. So this is a mixture velocity, not superficial velocities, against volume fraction. And this is some work we did where we had water and not oil, but an ionic liquid, which is a quite viscous other phase that does not mix with water. And we try to study the various patterns. So it doesn't quite matter these numbers here. I just want to show you the different patterns you can get. And the very common one is this plug flow. I have another better photograph image of this here because we're going to talk a bit more about it. It appears in a large region of the map. And depending on what is the relative fraction of the one of the other phase, we can have annular flow. And the annular flow tends in liquid-liquid not to be this nice straight one with a straight interface that you get in gas liquid. It's more often, more possible to see this sort of there is some waving, some undulations on the surface. So this goes closer to this transitional flow as well. And the irregular here means, this is the other thing you might see in macrochannels, that your plug flows are well established. Once you get to these regions here, you might see one pattern for a long time, and then that changes to the other pattern. So this is what irregular or transitional means here. We might have a nice annular flow, and then we might see some plug, or the annulus is interrupted, and then it starts again. And then at at this, when we have high volume fractions, in this case of the ionic liquid, we see these drop flows. So the plug flow is the one that we're going to talk more later on, and I'll show you some more properties of the plug flow. Is this characteristic shape? We have is the equivalent of the Taylor flow in gas liquid systems. We have elongated drops that are actually not touching the wall. There is a thin film, and we can go to that a bit later on. But there is, in the majority of cases, there is a thin film separating plugs from the wall. If the plugs are shorter, then we have drop flow, and this is kind of difference between the two regimes. So the characteristic size length of the drops here is larger than the tube diameter. We like them. We work a lot with them because they occupy a big area in the map. So we know we can get them for different conditions when we change the fractions of one phase or the other. And also, what we have seen, what people have seen and we have seen, is that we get these circulations happening inside the phases. So remember, this is all laminar flows. We depend on diffusion. So basically, these circulations break the thickness, because now we don't have to diffuse from here to here, let's say, but we have broken it into smaller regions. The same here and here.
Is just a motion of mixing, or is there direction also?
Okay, that's a good question. So how do we obtain these circulation patterns? It is, if you sit outside your tube, yeah, as an independent observer outside, of course, everything moves one way, yeah? So that the plugs stay here, they will go with the flow. However, if you take off the average velocity, and there are kind of slightly different ways to calculate that, then of course you get the circulation pattern. So if you now sit with the plug and you travel with it, you will see this circulation. Okay, so that's how you get these circulation patterns.
That is fine.
Yeah.
Direction.
Uh,
The above and below are reverse.
No, because here they both go in the middle this way, and then they go like that. Yeah, in the middle, the flow moves this way, and then it goes like this.
So in the center, there is no circulation, right?
No, this here, no, because that's the two vortices you get. Yeah, yeah. So so this is plug flow. Just a quick comment here that again, we are in a scale where surface phenomena are important. So whether you form in gas liquid systems, more often than not, the liquids will wet the wall unless you really go to extremes. In liquid systems, either phase can wet the wall more or less. So there are cases where you may not form the film because the wettability is not good enough. Okay, but in that might actually confuse this pattern so that you don't get these nice shapes that you get if there is a little film, thin film on the wall. If there is a thin film, then you get this very nice shape here on the front of the back of the plugs. So talking about flow patterns, what I wanted to show you is a little bit again, continue with the effect of the wall. And this is something from data we collected. We do use microfabrication for some of the channels, but having in mind also on what is easy to do and how do you eventually scale up at some point, we also use a lot of tubing. So instead of microfabricating something on a wafer chip or on a glass, we just buy capillaries. Yeah, so a lot of the results I'll show you are from capillaries. All the work, the microchannels are capillaries. And you can find actually capillaries that are, in this case, they write it here. This was from 250 microns capillaries results. And what we did is that we used different materials. Two of those are plastic, polymeric, and one is glass. And this is again for our ionic liquid water flow patterns, fluids. So you can see, and again, I won't go into detail. One thing I'll mention only, but that actually the material of the wall can play a role. And as you would expect, the two polymeric materials are a bit closer, while the glass one gives quite a large difference. And what is not so good in this case is that the glass one is the one that gives the smaller region of the plug flow. In these cases here, the ionic liquid was the continuous phase and the water was the dispersed phase. Okay, and what we say is that we only managed to have the water as the continuous phase when we use the glass channel. And even there, just to complicate things a little bit more, in these small channels, the way we started the experiment played a role on what phase was established as the continuous one. Because when you have a microchannel, if you've done an experiment, you have to think, how do I start it? Often you start with one phase and then you introduce the other. It's an option to start with the two together. With this, let's say, protocol of how we start can affect what pattern forms. And in this case here, yeah, we had to start with water. And in that case, only we managed to establish that as the continuous phase. So there is a lot more in this scale of how we end up with these flow patterns. And just one more thing I will show you is, again, trying to generalize the flow pattern maps, as others have done for gas liquid flows. Doesn't matter so much these things. This is a different system we used. I will a little bit about it, but all I wanted mainly to show here is that the coordinates we used to represent the flow patterns we found. And these are coordinates that were suggested, we did that in our lab, but these coordinates were suggested in this paper as well by Zhang and Tal in ChemEd's journal. So it is a rich topic. There is a lot of things happening. If you are interested in studying flow patterns, two-phase flows, there is a lot to be done. The transitions are important. If you are interested only to use the flow patterns to do a certain reaction, let's say separation, then there is also a lot of literature with different fluids to try to see what should be expected in your case. This is what we also do often, that if we want to do a certain reaction separation, we don't necessarily go to study everything. But from previous, let's say, experience or literature, we say, okay, if we want plug flow, we need to stay within these flow rates, within these phase ratios, and we're okay. Of course, as a hydrodynamic study is also very interesting and a lot more on the modeling. I will mention it very briefly here, but we are going to talk a lot more about it when we do mass transfer. The system we used here is what we call an aqueous biphasic system. You may have come across it. It's also very useful in pharmaceuticals we're discussing in the morning. So basically, it is two phases, but the way to form them is that you put in your water phase more conventional, let's say, some polymer and some salt. And above certain concentrations, this one phase separates into two and forms what we call an aqueous biphasic system. Both phases are mainly water, which is very good from environmental sustainability point of view. We don't have organic solvents. But of course, you have to play with the concentrations of the polymers and the salts. What we used in this case, since we are working a lot with ionic liquids, is that we use not a polymer, but ionic liquid instead of the polymer. And we managed to get again these two phases. You see here a nice plug flow. And we try to do this flow pattern map based on these coordinates, as I said. And basically what we have is this region here, which is mainly where interfacial tension forces dominate. That's why we have plug flow. While when you're outside, it's inertial forces or inertial viscous forces that dominate. So this is a more crude, let's say, representation of flow patterns, but at least it gave us the region of the plug flow regime we were doing our mass transfer. Yes.
How do we decide these coordinates?
Okay, so there are a lot of ways to do that. I think the first is to try. The first is to check the literature, what others have done. And then the next is to try your own, let's say, approach to see what better fits your experimental data. If there is, you can do some modeling to try to play with these powers here, but you need a lot of data. And that's why if that is your aim of study, it's good also to bring in data from other researchers if you have availability, if they're available, because that makes your database even bigger. And then you can see if there are discrepancies. Most people will suggest something for their system, but the thing is, can that be predictive? Yeah. So that's why it's good bringing more.
Where we are using EMI, we can feed the data and measure it.
Yeah, you need to have, yeah, exactly, yeah. Or, but it's always good what you don't know. It's like doing dimensional analysis many years ago, which parameters to include. So the previous work gives you an idea of what is important, what plays a role. Do we need to include Reynolds number or not? Yeah. Or do we need to include capillary or not? So there's this sort of decisions to be taken. But as I said, the more data, the better. Often, that's what happened also in gas liquid flows. There is a lot of data for normal pressure, atmospheric pressure, gas liquid flows. So basically, I think predictions are good. Once you start going into higher pressures, for example, then it's where discrepancies start appearing. The same will happen here. The data is building, but of course, the more common systems, organic solvents, kerosene or water would be more data. Once we get into more complex different fluids, then of course we'll have to check. And as I said, the other thing here, we have seen it a lot in the microchannels. I had a student that was trying to do plug flow with ionic liquid water, and she could not get what the previous student had. But I used the same channel diameter, but we have the same channel properties. Okay, we should have thought, or she should have thought, but she was literally using different inlet sizes. The inlets that fit in the T-junction to actually give you the main channel, which is trivial in a way. If you know, you pay attention. If you don't know, then it can be missed on the design. And sometimes, because as I said, with these setups, we try to, we don't microfabricate, a lot of them we buy. It's often to decide what fittings you need to put your D-junction together, your main channel. Sometimes the fittings are not always available for the range of sizes you want. So there would be, actually, we'll need the power. This is very intensive, I think. Let me, let me try. Yeah, and yeah, I just have a very strange computer. So let me. Here, how far is that from my? Is there another one? Ah, there is one here. Thank you. Yeah, it's great. It's also it doesn't need an adapter. No, sorry, I don't need that. Is that on? Do you want to press? Yeah. Okay, seems to work. Okay, so yeah, so these are things to bear in mind as well. They can affect your flow patterns, especially in these scales. I'm going to plug flow now, and I'm looking at the time as well. I'll go a bit faster. So plug flow is something we can go a little bit over, can't we? The half hour. Yeah. Okay. Plug flow. This is the pattern we spoke before, and I told you these characteristics. So what we have is the good thing is that it's very regular, and it does get very regular. Actually, this is observed experimentally. We can have something that is as good as that along the channel, and it's these internal circulations that are actually good for us. And it has high specific interfacial area, circulation patterns improve even more the mass transfer, and it's easy also to model. And yeah, some results with this one, as we increase the mixture velocity, we see our plugs get shorter. So what I will show you is a summary of results that are available. When we have plug flow, for mass transfer applications, we need to know the interfacial area. And the interfacial area depends on the size of the plugs and the film thickness. Yeah, depends on this here and how long this is. So the size of the plugs is the one parameter that is the more difficult to predict. There are quite a few works out in the literature. Just copy paste the table here. You can find the references. We can say that this is the general equation that actually represents them. If people have worked with Taylor bubbles, you might remember there was a paper by Gerstecki or a couple of papers that basically said that the size of the Taylor bubbles depends on the ratio of the flow rates plus something. It's an equivalent type of equation, a little bit more complex. And what we try to do is to use what was available and to put in one equation, and the parameters take these values. Kerstec is here as well, depending for the different investigators. So plug length is an issue, and as I said, if you use a slightly different tubing to introduce your flows, you may end up with different plug sizes. So we can discuss that a lot more in the end. Let me go through my slides first. The next thing we might want to consider is the interfacial area. And the interfacial area is, there are many ways to do that. One is if you have images, you can read your images. We tend to assume that is the flow is axisymmetric. Simpler ways to do this is to assume that the plug has a certain shape, which is a cylindrical body with a half circle with circular ends, and based on that to calculate the interfacial area. And I have a way to do that here that takes into account the tube size. Yeah, this should be capital D. I can correct that hopefully. And yeah, the film thickness. So this is simply geometry. You can say that, okay, the main body of the plug is a cylinder. I know the area, and this is spherical caps, and I know the area, and I can calculate an overall interfacial area, which is fine. The one thing and that can give you now the specific area of the plug, which is the plug surface area of the volume of this, let's say, part of the plug flow. This is called the unit cell often. So one plug and one slug, because it's repeated, called unit cell. What is in all these cases important is this film thickness. And you might have seen a lot more work on film thickness. And there the theory seems to be a little bit more settled. It is good to have the correlations, because even if you can get, let's say, experimentally, the length of the plugs, it might be quite tricky to get the film thickness. In some cases, the film thickness is very thin, and these are just images. But if the flow rate was a little bit less, the film thickness would be much smaller. It would be very difficult to get from imaging. You would need really to push your system, maybe to have much refractive index fluids, to add some dye, to do a lot to actually get very small thicknesses. So to have correlations is actually good. So there are a lot of correlations. And again, that's why I mentioned the gas-liquid flows, because up to here, the correlations come from gas-liquid systems. It's a small history. You may have come across all of them. So you have some film thickness. Fairbrother and Stubbs had some. Taylor suggested a correlation. Brotherton developed it analytica, another correlation. While the capillary numbers are small, then just the effect of capillary number seems to be all right. Basilius and Kerr later on found that higher flow rates, these type of correlations were not enough, so they suggested this type of correlation. Even later, and I mentioned it here, there are others in between. This one by Magiola and GIAN in 2015 was developed for liquid-liquid systems, and that's why I give it to you here. And this is the correlation that contains both the capillary and the Weber number, or if you want to manipulate it, the capillary and the Reynolds number in this way. And by giving it in this way, we show explicitly the effect of the velocity, because the velocity is cancelled out here, so it's only included here. So there is a lot of discussion on the film thickness. Even the Bretherton's equation, for example, a correlation that was developed analytically, and it was true for very small capillary numbers. What people found experimentally is that actually it did better when we were at higher capillary numbers rather than at the lower ones. And that's because contains capillary number, contains surface tension. And the assumption was that surface tension was very easily affected by impurities and whatever else might happen at the interface. But there are correlations, and when we want to use them for calculating the interfacial area of a plug, we can use one of them. So we've done that in some work. It is a suggestion. The plug length is the one that might have the biggest uncertainty. So unless you have your own plug length data, and you want to use the literature ones, if you want to use literature ones, the uncertainty is can be large. However, for the film thickness, we are a little bit more certain, and especially if you go to use something a little more specific, like for a liquid case or the right range of the capillary numbers, which means that if you have a film thickness and some plug length from somewhere, other experimental correlations, you can calculate the interfacial area with these assumptions that you have cylindrical body and circular ends. Okay, just to show you some results now very quickly. This is again from the aqueous biphasic systems. We try to mention film thickness. This is delta, dimensionless film thickness against the capillary number. And again, as I said, there is a lot of correlations. The Bretherton one didn't do very well. We found better agreement with we also proposed a correlation based on our data. But actually, this Magiola correlation was not too bad from the liquid-liquid systems. And there were two, Magiola suggested two correlations. Oh, the correlation was applied to 0.5 and 0.8 millimeters. And yeah, the results are not bad. And here is what happens with the plug length. That's what I wanted to show you. These two systems here have different densities and different, mainly densities and surface tensions. And this is the different plug lengths we obtained. And the interfacial areas we then calculated. Why do we study plug flow? Some results here. We get very high specific interfacial areas. This is a number we got for the system I showed you before, while in mixer settlers, this is the equivalent numbers. 1,000 compares to 6,000, and in pulse columns, I get only 200. So we intensify in this case, if we have any two-phase operation that depends on the interfacial area, such as interfacial mass transfer, then of course we gain by increasing the interfacial area. And as we will discuss in 2 days' time, actually this increase in interfacial area is what makes the difference sometimes in the improved mass transfer coefficients. Other improvements we might get because the actual mass transfer happens faster is not as good or as large as actually this change in interfacial area. I'll mention two more parameters. One is the circulation time we mentioned. This is some results we got from PIV. You get the velocity profiles. You take out in this case, we took out the plug velocity, and you get these circulation patterns. If we know these circulation patterns, if we know these streamlines, we can actually calculate the circulation time. How much time does a material take to move around? Okay, and it can be done. You need to have this sort of detail. So if you have done safety simulations, also you can calculate it. What I want to show you is two examples here, where we have the circulation time. Of course, it depends. The streamlines are not so good also at the end of the plug. In the main body of the plug, it seems to be quite constant. And since I'm showing these results, I'll show you what happens also with these circulation times and these circulations in general as we decrease the plug size. So you get this pattern here, and you see as you squeeze the plug, as the plug gets smaller, the circulations get shorter. You know, the paths the fluids have to go through are shorter. This is in a 1 millimeter channel. And what we have changed here is the mixture velocity. So the plugs go faster. We get, though, the average velocity off, but because the mixture velocity is higher, we manage to form smaller plugs in the inlets. And this is the proof here. If we compare this dimensional circulation time with the plug length for the different channels, that's what we get. We get this difference in circulation times in different channel sizes. So as you can see, the larger channel has the longest circulation time. So this is an effect of process intensification in a way. When we are in the smaller channels here, we have very quick circulations, which means our mass transfer can happen a bit faster. So I will spend 5, maybe 10 minutes at most to just very quickly have a look at pressure drop. Which the first, I don't think we'll mention pressure drop again, but it's something you can measure. If I want, I think we had a question before about that. Don't know if it shows in this graph here, but to measure pressure drop, you can have with T junctions, the pressure port at one part of the channel and the other can be open, or you can have two pressure ports to get pressure difference. It's easy, especially if you don't have, with microfabricated channels, you might have to think of that in advance. For us, that in this case that we're using just tubing, it's quite easy to attach a tube, T junction, and get your pressure drop. So pressure drop can be important. One thing that is important is, as we will talk later on, is for scale up, because we need that to design our scale up manifolds. The other is to see what's the energy consumption, because at some point when we go to scale up, we will have this dilemma. Let's say, do we increase the channel size or do we add more channels? And one of the considerations could be the energy consideration. How much pressure power do I need to pump fluid in a certain channel size and how much, compared to the overall gains on mass transfer. So just some results. Pressure drop against volume fraction. This is for ionic liquid water, let's say, cases. What I want to show you here is that the different patterns can have slightly different effect on the pressure drop. The annular flow, this is annular with ionic liquid on the outside. It's very viscous. That's why we have a little bit higher pressure drop there. Plug flow, the other plug or dispersed, they don't seem to matter very much. And again, because we were discussing different tube materials, we said the glass is the only one where we were able to have water as the continuous phase. So you see here the pressure drop decreases very much. And for me, this is a good excuse to say that we can actually manipulate the patterns in the small channels in a way that would be quite difficult to do in a larger one, because we can play a lot with the surface properties. If we are able, or in this case, just by using the material we buy. And that can allow us to decrease pressure drop. This is significant. Of course, there might be other issues. Which phase do we want on the wall? How easy it is to obtain it? But for the same set of fluids, this is the pressure drop we get if we work on for plug flow on a glass channel, and this is what we get if we work on a plastic channel. The justification is easy because we've changed the flow pattern, but it's a good thing to have in mind. And I will have a couple of correlations for pressure drop. I may stay on the same thing, on the main thing, which is what people have considered to try to calculate pressure drop in small channels. How many of you have done any work on multi-phase flows in general? Okay, good. In large channels, small channels? Okay. Okay, yeah. Are you at all aware of pressure drop correlations or? In large channels, there is one holy grail is the flow patterns, the other is the pressure drop. Think of all the big pipelines people wanted to do design some years ago to move oil, gas, all of these things. Pressure drop is essential. So it is very important. So there are a lot of ways to try to calculate pressure drop into phase flows, starting from empirical, and some more semi-empirical or very simple, let's say, analytical ones. I don't have it here, but maybe I should have said it. In liquid-liquid flows, in most cases, we are dealing with water and some solvent whose properties are not that different. It's not like having a gas and a liquid. So these pressure drop correlations that assume average properties of the phases are very quick and they're not bad. This is if you want to do a quick calculation, just use what we call in two-phase flows, the homogeneous model, where you average the properties, total flow rate, and you can find a decent pressure drop answer. If you want to go deeper, as people would like to understand what happens, is then you try to develop correlations that take the particularities of the flow pattern into account. So in plug flow, what people have tried to do, and there is a nice work by Jovanovic on that, is that they tried to think, what is the plug flow? How does it look like? Let me go back to a shape. So a plug flow, this is what we call a unit cell, the continuous phase and the plug, and then next to it there will be the same one. They said the pressure drop will come from the continuous phase and from the dispersed phase. The continuous phase will be frictional pressure drop, and because we are in small low velocities, the Hagen-Poiseuille equation in circular channels is good. For in non-circular channels, there would be the equivalent one, but it's basically pressure drop correlations for laminar flow. In this part here is where the bigger debate comes in, and people say that we have to have a frictional part and a part that takes into account the fact that we have a circular bubble, the Laplace, we have to take into account the interfacial forces. So they split this part here into frictional pressure drop and an interfacial, let's say, pressure drop or a Laplace pressure drop. And if I go back to here, this is what we have. We have, let's start from here. We have the frictional pressure drop, the frictional for the continuous and frictional for the dispersed phase, and also this Laplace term that accounts for this having the plug in the middle and causing this disturbance in the flow that depends on the interfacial forces. So there are some ways to go about it, and all of them have some assumptions. If we want to calculate, as I said, the frictional pressure drop for the continuous phase, usually Hagen-Poiseuille equation is used, kind of this. For the dispersed phase, the frictional pressure drop, the assumption goes that it's the film that caused this friction because this is the one close to the wall. And then there are two ways or different ways to calculate what's the frictional pressure drop in the film. And Jovanovic suggested two ways. One is to assume the film is stagnant, and the other is to assume it's not stagnant. But the correlation was getting more complex. That's why I didn't write it here. Here I wanted to show you. This is the Hagen-Poiseuille equation. This is frictional pressure drop in the stagnant film, and this term here accounts for the pressure drop in the bubble. And this is actually coming from the work from Bretherton. Bretherton did his analysis to calculate the film thickness, plug velocity, they're related, and the pressure drop. So this term is coming here, and of course there's a bit of fitting just to make sure that we have correct correlations. So what we've done is that we tried to apply this correlation to some results we had, and we found that the predictions were not bad. We kind of manipulated it a bit because in this equation here, you need the film thickness. Okay, you need to know how thick the film is. H, if you have, it's the thickness of the film is the delta, but which you can either measure or get from correlations. And in our case, we did not use the Bretherton correlation that Jovanovic had used. We used our own film thickness correlation. So the predictions were not bad. The other thing, maybe I'll show it here very quickly and I'll stop to get some questions as well. A simpler way to go about it. Basically, what we said in subsequent work by Eduardo Garcia-Ortega is to say that the pressure drop in a unit cell depends on the what you have in the continuous phase, which is Poiseuille type of equation, and what you get in the plug phase. And this thing here can be all, because there are a lot of assumptions, is the one that needs to be fitted. The other thing that we did here that I've written is that if you want to have the average pressure drop in the tube, not the total, the average pressure drop, then because the flow is periodic, we can use this correlation to calculate, it's basically calculated from the pressure drop in a unit cell, because the unit cell is repeated. So the pressure drop that the unit cell gives you is the same as the average pressure drop in your tube. So went a bit faster in the end, I'm sorry. But that's all I wanted to say in this, let's say in this lecture today, to cover some details of the flow patterns and then some basic characteristics, especially for the plug flow that we will see more later on. Yeah, and that's all from me. So if you have questions or we can take it afterwards, it depends on how when we want to finish.
Take it during tea, and then we have duration at the department.